Hello, welcome to this video. Today we're going to talk about a Laplace circuit example, specifically how to get a transfer function, what's the meaning in the Laplace domain, and also how to understand a cutoff frequency in a simple circuit just like this. So for this example, we're taking into account something quite similar to what you're going to be working on the lab activity, which consists of a simple RC circuit that consists of some voltage input and some voltage output. So we would like to know the input-output relationship, meaning V out over Vn. How the voltage and magnitude relate in time for those two quantities. And that's exactly what we called as transfer function. How the circuit is going to be essentially transferring what input we're putting on the left side and what is happening in terms of the output. So let's go on this example. So we know that in this circuit, it's an open. So let's call this I2 of S equals 0. So we have just one current here going on, but called it I of S. So what we would like to get here is an expression in terms of S, meaning that we need to move this circuit into the Laplace domain, and we need to get the relationship V out over Vn. So to do so, first we're gonna the Laplace domain circuit is given by. So in this case, what we only have to take care of, it's essentially the capacitor. So as you have studied so far, the resistor does not change in the Laplace domain, such as resistors become real parts of impedances in the phasor representation. Same thing or very similar thing happens in the Laplace domain. However, for capacitors, we get SC, which, if you remember correctly, in the phasor representation, we use 1 over j omega c, right? That's how we transform it. So you kind of get the idea that Laplace, it's simply phasor representation using S equals j omega. That has a profound mathematical meaning. However, for practical purposes, it's simply this replacement. So we're going to assume that this voltage is in the Laplace domain, whatever that voltage is, and however it looks like, we don't really care much. And we have this current I of S. We already said that the circuit is an open circuit, so no element connected here. This current is 0, so we only have one current. So what we can do here is to say from this circuit, right, we can say B out of S, it's simply the current I of S times this impedance related to the capacitor. This current times this impedance is going to give us this voltage output. So based on that, we can say this times 1 over SC is going to give us V out. We have one equation, and another equation we can impose using this relationship, right? So we can say equation number 1, equation number 2 would be Vn of S minus R times I of S minus the impedance 1 over SC times, actually let's call it minus V out of S equals 0. We know most definitely we know that this voltage equals this voltage. So we're simply replacing. Now 1 and 2, and we get Vn of S minus, so we want to replace the value of I, right? So here we're going to say I of S, it's going to be V out of S times SC, right? So now we're going to replace that value of I, right, into this second equation, and we get RCS times V out of S minus V out of S equals 0. So we put everything together here, and we should we should have V, let's call V out of S equals, times 1 plus RCS equals Vn. So I moved Vn to the other side. We have all positive signs here. And finally, we can divide everything by V out. So we move this to the other side. Sorry, the opposite, right? The opposite. We want V out over Vn. So Vn, we move it to this side. And this element, we move it to the other side as a denominator. And we finally get V out of S over Vn of S, which in this case corresponds to 1 over 1 plus RCS. And this is what we called H of S. Transfer function. So what is this transfer function? What is the main purpose of defining this? It's essentially a way to multiply an input to give an output. So it's an easy way to work input-output circuits in this case, or any linear element or any set of equations in the time domain can be transformed into the Laplace domain such that an input, right, let's call it, an output, it's going to be simply the transfer function times the input in the Laplace domain. So this is quite important, right? It's the way we're going to be modifying the input signal to obtain an output signal. So that's very powerful. So the study of the transfer function is going to give us all the main behavior of the circuit in the frequency domain. That's why H of S, it's so important and it's massively studied, because you need to know how the circuit is behaving in terms of frequency when you have an unknown input. So you know, if I have this input, the output is going to be affected by whatever the transfer function is doing. So based on that analysis, now let's go one step forward and try to calculate something based on this transfer function. So one important thing related to this is what we call the cutoff frequency. The cutoff frequency is defined as the frequency, of course, in this case in hertz. When we talk about frequency, it can be hertz or it can be radians per second. So we can be talking about omega. But both are correct. The frequency where the amplitude of the transfer function, H of S, with S equals j omega, is 1 over square root of 2. Meaning Mathematically, this means that the module of h of j omega, so we're replacing s by j omega, the module of this transfer function equals 1 over square root of 2. So in practice, this corresponds to a decay from 0 dV to minus 3 dV. So whenever we reach those 3 dVs, we're reaching this condition. The amplitude of the transfer function is dropping to this factor with respect to, let's say, 1 in per unit, right? We call this, we also call this the half power point. So by the way, this is 0.007. You're going to see this number quite a lot. So the amplitude is dropping by about 30%. Right? It's dropping from 100% to 70.7%. That means that the power that is delivered to the, let's say, output, it gets halved. Right? Power is going to be this square, so if this is square, the power is going to go down by half. That's why it's half power point. So let's apply this definition to our case. In our case, right, we're going to have let's do this. 1 plus s, we change it by j omega RC equals 1 over square root of 2. And this at this point should be very familiar for you. Now we're in the something similar to the phasor representation, right? We're familiar with this j omegas being around, and now we need to find what is the amplitude of this phasor, right? So essentially the amplitude of this phasor will be the square root of, let me write it down. I don't know how to say it actually. So it's going to be 1 square over 1 square plus omega c square r square c square and the square root, right? Basically we have 1 over, let's call it a plus jb, and we want to transform this into magnitude. What is the magnitude of this phasor? If you do this operation, then you're going to get to this definition equals to 1 over square root of 2. So then solving for omega c, you get, so I'm going fast here, I don't want to go through all the math, but the main steps, you can actually validate this later on, that we're actually taking the steps and going here, it's going to lead to this. So that's definitely the case. So I encourage you to work the middle steps here. So now the same thing, we want to solve for what is the cutoff frequency that achieves this condition. So you have to solve this equation in terms of omega c, right? So if you do that, you solve this equation in terms of omega c, you should get to omega c equals 1 over RC, right? So we know that this is 2 pi times FC, that's 1 over RC. So finally we get FC equals 1 over 2 pi RC. That's the cutoff frequency of this transfer function. Now, what does it mean in terms of the body plot, for example? And we can quickly glance through it. So this transfer function has one pole on a negative value, right? S equals minus 1 over RC. So based on what you have learned on the lectures, we can very quickly depict what is going to be the body plot, the magnitude body plot for this. We're going to go through in a following video through how to actually measure this body plot in terms of magnitude and angle. But let's follow up. So this slope is going to be minus 20 dV per decade, right? And we have around here, this should be 0 dV, and here we're going to have minus 3 dV. And this frequency, it's going to correspond to the cutoff frequency, okay? So why is this important? Because it allows us to know, one, what is the frequency that it's going to achieve half power. So before this, we have more than half of the power on the output side. After that frequency, meaning for frequencies higher than the cutoff frequency, we're going to have less, even less than half power. And it also allows you to identify this knee point in the body plot. So overall, this cutoff frequency, it's very well known, used in practicality. So I encourage you to always keep that in mind. It's going to be important for the lab 2 filters that we're going to be studying, and it's going to be important for understanding the concept too. So now we're going to go and move to the next video. Thank you.